Good morning, everyone. It is 9 a.m. here in France. We are supposed to be live streaming, so I think for those of you who are watching this from a distance, well, I want to welcome you as well. My name is Jan, and I am in charge of the Scilab business unit in ESI Group. For this first presentation, I want to welcome everyone to the Scilab community. For that, I would like to go through a brief history of Scilab. It is a story about software and science, but above all, it is a story about men and women. This introduction in the beginning is about thanking everyone who made this event possible. I want to start by thanking ESI Group for organizing this Scilab conference, in particular Laura and Gaël and Aurélie, present here today with us. Good morning, Laura. And I also want to thank Mozilla Foundation, in particular Sylvestre, who used to be part of the Scilab team. And thank you for inviting us in this wonderful location in the center of Paris. Finally, I want to thank all of you for being here, especially the speakers. Here, as you can see, we have a very full agenda today, and so I'm delighted to have you all here today. Let us shortly go back in time. What you see on this picture, it is the last community event we had in France in the very same room. It was in 2015. So, this is a short summary of previous episodes. It was a very successful event. The three best presentations of the event were based out of the votes of the audience. In the first place, the French Nuclear Agency, CEA, presenting on their migration from MATLAB to Scilab. Second was from our Italian partner, Evidence, on state machines with Scilab and Excos. And the third one, from the French Space Agency, we have them today again. So Alain and Thierry, you will be presenting further some space missions. Today it's Mars. Last time it was about landing on the comet. It was a very successful event, and we had every year before this one, user conference called ScilabTec since 2009. They were organized very professionally by Julie, who was in charge of the communications in the days at INRIA, the French research. But I'm not going to lie to you, the last 3 years have been quite challenging. Even though Scilab goes back a long time. Its origins are coming from the 80s and the 90s. And its expansion goes far beyond our small team. So here is a short timeline of the three main steps, I would say, of our history up until today. Now I want to go through this short history of time with you. First, Scilab started formally in 1994, and its premises are going back to the expertise of INRIA. INRIA is a French research institute for computer science. In this research center, in the Paris area, we had a team of giants, as you can see in this list, who paved the way for a large scientific project. I was lucky enough to meet two of those giants, Serge, who some of you might know, he was presenting at the last Scilab conference, and Claude, who operated the transition from INRIA to Scilab Enterprises. In 2003, there was a first Scilab consortium whose goal was to drive the roadmap of the software. Those are the founding members from the French elite. And since 2008, our goal was to industrialize the development of Scilab, to conduct a transition from the research to a large industrial adoption. A new generation of computer scientists took over the development of Scilab. Today we have some of them, Clément and Antoine. Antoine, who's the architect of Scilab and our oldest team member, will be joining us. He's been around for 10 years now. So thanks to those talented software engineers, we were able to make a solid and robust software. I'd like to remind you that 2008 was also the first version of Scilab 5. Today we are at Scilab 6. So as the industry was starting to adopt Scilab, there was a rising need for services around the open source software. And it was the very reason for the creation of Scilab Enterprises. The whole development team switched over from INRIA to Scilab Enterprises in 2012. And we soon figured out that from the expert usage to the development of application, our main competitor was actually not MATLAB, but it was rather Excel. So we figured out that lots of our main users were packaging together data with algorithm and developing on top a graphical user interface in order to develop what we call application. This is also what led us to Scilab Cloud, to a new technology and an underlying business model for the deployment of application. It was in 2016. And today you will see a presentation from Sanofi, from Jean-Pierre, about the very first industrial use of Scilab Cloud for energy consumption in the pharmaceutical industry. But around those times, we also had very important research projects which were enabling to develop Scilab further. I'll quote just some of them. Colloque was led by Cédric in our team, and it was to stay close to our friend in HPC, high performance computing. Another very important and major project for Scilab Enterprise and for Excos was Argo, and it was brilliantly orchestrated by Clément. Today you will see two presentations, one from the German Aerospace Center on control system for flight simulator, and just after my presentation, one from the Fraunhofer Institute, the very same Fraunhofer Institute who invented the MP3 technology next to Nuremberg. And today they will be presenting you image processing. There's even a demo backstage. One last research project that I wanted to quote is Megasif. It was a very first taste for us of what is finite element analysis and the development of reduced order modeling. It was a foundation for our future, as we got closer at this time already to ESI Group. And from that time on, we also saw a new generation of promising engineers, Hughes, who is with us today, who has a strong expertise in the domain. So if you have questions, don't hesitate to ask him. And you will see also a presentation from one of our partners, Bertin, later today, from Sophie. So it ends up with the question, why ESI at the end or the beginning of this journey? Why did we join ESI? So to give you some perspective about the simulation and analysis market, it's a $6 billion market, and it's quite strongly concentrated. As you can see, there's just a few players that are taking it all, basically. ANSYS is number one, and closely behind you can see that MassWork is also leading with close to no competition at all, almost. But in both cases, there's a very strong academic footprint, and it creates a natural barrier of entry, unless we have a value proposition that is highly disruptive, around open source and that can challenge this status quo. So who's ESI? In a few slides, I'll try to introduce you to this pure player of the simulation market. What is smart virtual prototyping? The differentiative proposition of ESI is to go from analysis, simulation of simple physics, thermodynamic, structural analysis, and so on, until virtual testing, taking into account the manufacturing effects. And this is what produces a virtual prototype. Now, the next step now for the future of ESI, and it's also the reason why ESI acquired Scilab, is to go to smart virtual prototyping, meaning that it's not good enough to have an analysis of the product conception, the design phase, and engineering, but it's very important to see this product in operation, in service, and to assess its performances all along the product life cycle. So this is a short overview of all of the technologies that ESI is developing around 3 pillars: engineering, manufacturing, and in-service. And early on, since 2012, ESI already showed an interest for open source through the acquisition of the OpenCFD team developing the OpenFOAM software for CFD, for computational fluid dynamics. So this acquisition goes along with this strategy of building technologies and not only product, but also services around solutions. As a summary, today ESI is it's not that big of a company actually. It's around 1,200 people worldwide, but it's fairly largely spread all around the world. And it leads me to the last part of my presentation on Scilab all over the world. So I started to work for Scilab about 5 years ago, and in the first place, I was supposed to develop the business in Germany. We organized, with the help of Jürgen Koch, a professor in the area of Stuttgart, a Scilab conference at that time, and some of the people that were presenting will be here today also. You will have a presentation from Hochschule Esslingen today. We have very large activities at the moment in Japan. As you can see on this picture, there's already a strong competition happening. And well, we had a first meetup with a small group, a small representation of the community last year already, and I actually just wrote this presentation on the plane back from Japan. So India is also a very large user of Scilab. Just simply in the academia, I want to thank Kanan Mugdalia from the IIT Bombay, who has been spreading the use of Scilab. Thanks to him, you can see on this chart, there's around 240,000 students that were trained with Scilab. It is actually more than Python in engineering school. So here, this is the spread over the years. And this year, in August, we had a conference in India, and this is Professor Kanan Mugdalia presenting around the open source supported by ESI on OpenFOAM and Scilab. And obviously, friends, we won't forget our roots. There's a very large community, also lots of academics. Every year, there's around 30,000 students from preparatory classes, from engineering school, from the university that are learning Scilab. It produces sometimes some funny results. When I have a look at the social networks, sometimes I stumbled upon such funny tweets. So this is also the new generation speaking, I guess. And in the US, well, the US is it's a bit difficult, to be honest. I would say it's MATLAB land. But something funny happened. It was in the beginning of 2017, as we were joining ESI, and we saw this post. So we decided to contact John, and yeah, I'll tell you a bit about John. So John Eaton is the member of the Resistance, I would say. It's a founder of Octave, and those are a few slides from him on Octave. So why the name Octave in the first place? It was a reference to a professor who passed away last year, and those are a few, in a few lines, the origin and the history. Actually, Octave started out as some sort of a textbook companion on chemistry, because John at that time was studying chemistry. Well, the first release, 1994, might sound familiar to you. It's the same year as Scilab. In 2002, the book that was supposed to go along the software finally was published, but well, the software was already growing and in a direction that surprised John in the first place, because it did not intend to make a clone of MATLAB at the first place. And so, if you look at it, this is the scope of the project. So this is actually a photo from John. He highlighted all of the functions that he found in the first manual of MATLAB, and he was just trying to, implement all of them. And he saw at that time, well, it cannot be that hard, Look at it. Well, now it's a bit more challenging, I would say. So it made us also meet new people. And here today we have Botao, who will be presenting, coming from the US. So thank you very much for coming all the way, on the use of open source in an enterprise computing environment. But let's go back to Scilab and the usage throughout the community. I have a few slides, 3 slides on some statistics here. This might interest you, just to have a look at the different application field where Scilab is being used. Those data are coming from form. When you download Scilab, you can fill up a form. You don't have to, but you can. And here we have a sample of around 100,000 downloads that filled out this form. So in the first place, there's a lot of users using it in electronics. Second is data analytics. And mechanics is coming in number 3. Now, in terms of domain, including the education, as you can see, education is very strong. So 63% of our users come from the education, and the rest is industry. And those are the different industrial domain where Scilab is being used. So research is in yellow. It's very strong also. And afterwards, you have a lot of different fields. So I'd like to conclude this talk to now talk a bit about the future of Scilab. And here I'm actually adding a graph that is coming from a feedback of a teacher. He has been using Scilab for 15 years. His name is Klaus. And those are the kind of things that give me motivation to keep investing efforts in Scilab, to see so much things produced by the community. Now you might wonder, where are we going? And this is also the purpose of the final talk of today. But here in one slide, I'll try to sum up our strategic targets for the future in terms of who are we going to aim at. In the first place, obviously, we will want to bring additional value to existing traditional simulation user. Here, making a competition to ANSYS and not MATLAB directly, but trying to bring in different domains such as CFD, so computational fluid dynamic, some model reduction technique, in vibroacoustic, bring some optimization. Those are some of the projects that we've been doing in the past 2 years, and some system model deployment. The second target is obviously system simulation engineers, so in competition with MATLAB. And here our value proposition is to embrace open source to unlock the engineering productivity that goes along with it. So if you have additional resources that will join your team, well, you'd better off using an open source software that can scale with your engineering needs. And obviously, in the automotive domain, model-based design is big. In the signal processing, also for chip design, as you will see later today, there's a strong need for that. So in both domains, whether it's control system and block-based diagram or scripting, this is something where we want to grow bigger. And the last part that we don't want to forget is about application developers, and to provide them as a, well, I said competition to Python, but really is there a competition when we're talking about open source? It's mainly to bring and discover the potential of simulation, what goes around mathematics, optimization, statistics, signal processing, and control system, to bring all of those value to fields that are new to the simulation, mostly. So if you look at some of the presentations that we will have, for instance, from Sanofi in the pharmaceutical, this is a field that is not as mature as aerospace and automotive. And we also have lots of examples in process industries, for instance, in risk modeling. So those are domains where there's a very large potential to enlarge the use of Scilab. Thank you. So without further ado, I'd like to call upon stage the next presenter, Michael Schäuberle. Did I pronounce it right? Almost. Doctor engineer from the Fraunhofer Institute for Integrated Circuits. He's the head of the group for imaging solution. Dr. Michael Schäuberle. Schäuberle? Yeah. Great. Okay. It's received a diploma in electrical engineering with honor in 2006 from the University of Erlangen-Nuremberg. He then joined the Fraunhofer IES and started to work on high-quality imaging systems in the electronic imaging department. In 2007, he joined the University of Erlangen-Nuremberg to continue the research on algorithm for high-end camera system in a close cooperation with Fraunhofer IES. In 2013, he received a PhD with honors in electrical engineering for his work on digital cameras. After working as a chief scientist in electronic imaging, he is now head of the group imaging solution at the Fraunhofer IES with a focus developing and implementing novel imaging technologies. His motto, beyond human vision. That's nice. So we are ahead of schedule. You can take your time. You have 30 minutes.
Okay. So welcome from my side as well, and thank you for the introduction, Jan. Just to give you a little background where I come from. So Jan mentioned already from Germany, from Erlangen, and I come from one of the Fraunhofer Institutes in Germany. This is an applied research organization, if you haven't heard about them yet. Altogether, it's around 25,000 people, and our institute is one of the larger ones with around 1,500 people involved altogether in this institute. And in this institute, we have many different fields, and the group that I am heading is focused on imaging. So we're doing imaging technology. It's not that much about processing the final image, but about making images, generating images. And that's where my motto and this topic comes from. The idea is to do something that is beyond the human eye, to go further and see new modalities, new technology, and new things that are out there in the world. Today I will talk about the topic polarization imaging. That is something that people might know if they have photography and turn a polarization filter to suppress reflections, for example. But polarization is so much more in discovering new properties of materials, of analyzing materials, and in a close cooperation with Jan and other partners from the Argo project, we can now present a result where we can go through the whole chain, starting with Scilab and going all the way to an industrial application. This is work from people of my group today. I brought two colleagues, Koray and Stefan, are also here in the audience, and they can later show you the demo. So this is the green one lighting, green glass over there. I hope you will understand what's in there throughout the presentation. I will talk firstly about polarization of light. So what is behind that? What does that involve? It might be familiar to some of you if you studied physics. In other disciplines, it's maybe not that common to know about that, so I will give a brief introduction. I will show how to measure polarization, how to derive values from that. I will show how we do algorithm development and show the final product or the final chain of what we developed, going from the development to the product in the Argo project and with a demo, as we've seen over there. And the application of the image you see here, this is a drinking glass. This is a special type of drinking glass, and we are looking at the stress in these drinking glasses as one example. More on that later. Let's start with at the very beginning. Light is an electromagnetic wave, and light has a certain property. For example, the amplitude of this wave. This is something we perceive as the brightness of light. So if there is more, then we could draw a wave with higher amplitude. If we change the wavelength of light, this is something we perceive as color. So red or blue is simply different wavelengths in light. And this electromagnetic wave has another property. It's the orientation of the waves. And this orientation, this is something that is mostly not visible to the human eye. And this is the effect of polarization. In typical light sources, mostly the orientation is equally distributed. So have waves of all kinds of orientations, and this is something we describe as light that is not polarized or has a degree of polarization of 0%. If we pass the light through some effect, we will see later, it's possible to get light with a very strong orientation or very high degree of orientation. And we describe this as a degree of polarization of 100%. So most or all of the light rays are polarized in a certain orientation. There's something in between, so you could have partially polarized light. You could indicate this by having many in a certain direction and some in the other directions, for example. And we could also measure, on the last line here, the dominant angle of the polarization. So we can say, oh, it's polarized horizontally or vertically or at any other angle you would describe. And the first question comes, where does this come from? Why do we have polarization? What is the effect? If we look at natural light sources, let's say the light from the sky, the light from a light bulb, from a fire, all of those light sources are unpolarized. So all directions and orientations are present in that kind of light. The only exception is that in lasers you have polarization by nature or by how it's generated. But if light is unpolarized, why do we talk about it? There are many effects that can cause the light to go polarized. So, for example, if you have reflection on a surface, let's think of a water surface, if you have a piece of glass that reflects the light, if you construct a beam splitter that splits the light into two beams, this is something that gives you polarized light. So on the right you see the example of a surface with different refraction index, and the incoming light from the upper left is split into two rays of light, and those rays of light are, one of them is horizontally polarized and the other is slightly polarized. So this gives you a strong polarization, simply by looking at a reflection of a surface. In nature, this is something that is, for example, in water, very important. So some insects are able to look for polarized light, fly there and try to lay their egg there. So they see the polarization and try to detect water bodies and to lay their egg. So they're not trying to find the color of water or the shininess of water. They are simply looking for the degree of polarization in nature by flying around and then laying their eggs where the polarization is high. We can use this, for example, in surface inspection. So if you want to have a coating on a surface, want to have flatness or something, this is something where this effect could be used. And this goes much further than just polarization. It's a whole domain of ellipsometry, analyzing the reflections. There is also something that reflection at non-metallic surfaces. You have something at the human skin, that is at plants, at plastics, and this is something that can help in object classification. So if you want to sort something, if you want to detect different parts of a plant, for example, you can use this effect to classify or to help classify and use this as an additional modality to segment a plant, for example, in image processing. Another effect that causes polarization is nanostructures. So if you have something that is structured in the range of the size of wavelengths, this can create polarization. This is something that is used in transmission or in reflection as well. So let's say if you want to create polarization filters, there is one type of filters where you have a wire grid. So there is small wires, so to say, in the order of the size of the wavelength, and those cause the light to be polarized, so polarization filters. There is another application that we found that is the inspection of carbon fibers. So in carbon fibers, this is also very fine conductive material, and this material causes the light to polarize. So I shine unpolarized light onto my fiber, and I get back polarized light. So the setup you see in this image, this is simply a ring light that shines down onto my surface and a camera looking down at my object. And if I do this with regular imaging, I would get an image like this. So this is a woven pattern of fibers. So it's a bundle of fibers interwoven with another bundle. And this is a prefabricated material, like a fabric, that is used, for example, if you want to fabricate some components, let's say a rotor blade or a car component. Then you take these fiber cloths, fabrics, and put them on top of each other and press them together. And what is important about those is if you want to look at the strength of a material, then in carbon fibers it's very dangerous if those orientations are wrong. So if they are wrinkled or if they're shifted or distracted, then this causes the strength of the material to go down. In car parts, you also have the problem that if you want to have this as a surface, the customer pays quite a lot of money to have a nice surface. So you want to make sure that the surface is nice looking and regular and symmetric. And if you would start with an image like this and wanted to do image processing to check if this is properly oriented, you would have quite a hard time because this material is black from its beginning, so it's not easy to do imaging with black material, and then lighting it is very difficult because you get a lot of reflections, and finding the orientations of fibers, I would say in this image it's quite challenging or even impossible to do that. If we take the same photo or the same image with polarization, we would have another modality to work with this image. And this modality would give us something like this. What we encoded here is the angle of polarization, so the angle of the light that comes back from the fiber as color. And this image is enhanced with color, and we can easily see that the fibers in this case are not closely together. So in the spaces between those, there are gaps, and they would not even be, you cannot observe them, or very difficult to observe the gaps in these cases here. And this is very easy to be done with polarization. So it's a quick inspection that helps quite a lot. I didn't do anything. Okay. In inspecting carbon fibers, for example. There is another effect that is the scattering of light at small particles. So this is another effect that animals use. The particles in the sky cause the light of the sky to be slightly polarized, and this helps some animals navigate and fly in certain directions. But this is also for particle analysis in the scientific sense. The effect is that the light that is reflected from a particle in a right angle, this is fully polarized, and light that is mostly the same direction that goes on unpolarized. So another effect that causes polarization. Another effect is the birefringence in optical anisotropic material. So it does not have the same optical properties in different orientations. And this is a material, for example, there is some quartz material, some calcite, some stones that exhibit this property, and they cause the light, after passing through, to be split up into two properties, two rays of light. This is an effect that is also present in glass and plastics. So in transparent plastics and glass, the light will change its property if it goes through, and will have different polarization properties afterwards. And this is an effect that we are using in inspecting glass. So what we have here is an example similar to the setup we are showing back there. The idea is you pass polarized light through the glass, and the glass is able to modify the polarization of the light. And after that, you can detect and measure the polarization and directly see, for example, areas of stress in this glass, where the glass did not cool properly or did not cool as intended. And these areas can be identified, and the glass can then be checked if it's good or bad, so to say. So to give you an idea, with polarization, there's many fields that open up and that can help you do more than just looking at the things. It gives you more information about some objects around you. And this is a method we are using and working on and trying to extend. So how do we measure polarization? The basic principle is we have more degrees of freedom in polarization, like at least 3 or maybe 4. It's not just the intensity, as I mentioned, but it's the degree of polarization, the angle of polarization, and there is the intensity of circular polarization. So it's 4. Right now we are using 3. That is sufficient for many applications. And for doing this, you need at least 3 or 4 measurements to do this. And the most basic way is to use a regular camera and use a filter in front of the camera and simply make 4 images by rotating this filter. Basic principle. This is not really nice because you can do that if you have the time to do so. If you want to go to an industrial application, it's maybe not the best idea to do that. You can do that quicker, not rotating, but doing electronic shutters, but that has its own problems with temperature drift. You can do that with side-by-side cameras, using 4 cameras with fixed filters, for example. And there are many different variations of doing that. Having line scan cameras, so if you have an industrial process on a conveyor belt, you might use multi-line cameras to scan polarization. You might use something that uses beam splitters, so one optical path as the image shows, but with optical beam splitters, that makes everything quite expensive. But those are solutions that were available in the past. In the last couple of years, we've been working on one approach that we call the division of focal plane. This is an approach that is very similar to how most color cameras work today. You simply have one pixel that is sensitive to one color, let's say green, and the next pixel is sensitive to red only. So you treat in some spatial resolution of the sensor for getting another dimension, let's say color, or in this case polarization. And the image on the top right shows where you put on polarization filters, like for the analysis. And one pixel has the filters with this orientation, the next one has this orientation, and so on, going through all of those pixels. So the camera in the end will have smaller resolution than a native black and white camera, but it will have all of those properties in there. And to do this, you could glue on such a filter to the sensor. That's maybe for a first test. This is not practical for small pixels for modern cameras. And the idea is to use nanostructured filters, embedded them directly into the CMOS fabrication process. So on the bottom left, you see such a pixel design from a couple of years back, where you have these nanowires as polarizing filters directly embedded into the pixel design. And if you build such a sensor, that's what you see in the middle, and make a camera out of it, you have a camera that is able to measure polarization in just capturing a single image. And that's how we started and how we developed this technology. And we are in the lucky position that we found something very interesting that big players are now catching up to do. Sony has released a polarization sensor with 5 megapixels. So even if the native resolution is 5 megapixels, and take something away of that, it's still enough pixels left to work with that. And for those sensors, we are seeing cameras to appear from most camera manufacturers. Some of those cameras we have already working and have them in the lab. Some are only announced so far. And we brought one of those new cameras, in this case it's a Chai camera, with us. And we had a head start to work with those. So we have software and algorithms and have been working on those to go further. So what is necessary? What is the challenges you need to do with that? What is necessary to do with those cameras or with these images? First of all, you have, as I mentioned, the pixels side by side. So one pixel is sensitive to this orientation, and the next pixel is sensitive to a different orientation of light. And you need to do some processing to reconstruct a full image. And this is something that has been solved in color imaging for doing the debayering, the demosaicing, color reconstruction. But in this case, the problem is slightly different because the correlation between the channels is different from color imaging. So that's something you need to solve as a challenge, how to process this raw image. There is not much research on that. There is not much standards or established algorithms for this. Next challenge is, how do you calibrate those cameras for measurements? Right now on the bottom right, this is a colorful image, but in the end you want to do measurements. You want to put a number to it and you want to say, this has this much stress in the image. So you need to go through the whole chain of calibrating the camera, the raw data, make it stable for temperature, and produce a final image or a final measurement results. And what we are currently focusing on is, in the beginning I've shown many different applications of what you can do with polarization, and what do you need to actually make this image good. So you need to have a certain arrangement, a certain kind of illumination, a certain kind of combination of filters and lights, and this is something that is very different from one application to another. In the end, the user is usually not interested in saying, oh, this is a degree of polarization of 25%. The user usually needs to have some classification. He needs to know, is this a good or a bad glass? Is this something to get a measurement in the end, not the polarization value. So there is much more processing involved to get to an answer for the customer. We started in algorithm development in the Argo project, or before the Argo project, but also in the Argo project, and we analyzed different ways of doing the image processing. The idea is we wanted to evaluate different types of calculations, different modes of working with the images, and we did this in the following setup. In the beginning, we just used a regular camera on the top right, just a regular off-the-shelf industrial camera. We had a rotating motorized filter on the camera to do the sequential measurement. And for example, on the bottom right, this is a light source with a polarization filter, a glass on top. And we started using Scilab for this. And there were two challenges. The first challenge was that if you take an industrial USB camera, that is something that is not supported right out of the box. So you need to extend to get industrial imaging live into Scilab. And this is a module we worked on. We worked on for one camera type. And what we were able to do is we were able to capture live images and do a live processing of industrial image camera, go into Scilab, do processing, and display the results. Another module we wrote in this case was to control the motor. This was a step motor controller to interface it. And with those, we were able to have an interactive demo setup. Looked very similar to this one, where you could tweak and turn around and hold the glass in different orientations and get a live image to work with this. And this is an important step because if you make one image and then you go to the processing and type in something, and let's say even 20 seconds later you have the result, it's very hard to tweak and turn around your setups and modify. So getting to the interactive workflow was a very, very major step for us to analyze objects. So you have to imagine you get a sample from a customer, it's some object you have never used before, seen before, and you want to see, is there some defect maybe here, or if you turn it like that or that. So it's quite a step of sitting in the laboratory and working with those objects, and an interactive working is interesting here. The processing we implemented is something we take like the 4 raw images from the camera. There is all of the calibration, the calculation procedures to get to the Stokes parameters, so the first defined set of polarization description, and then go further from there, let's say to calculate retardation in the glass, magnitude of stress, orientation of stress in the glass example. The demo I will be showing over there is then the next step, how to get to the product development. And in this case, we were very lucky to have this Argo project, as mentioned, and with this combination of tools, of partners, we were able to have a very nice chain of going from the algorithm development to the product. The idea is we are using and integrating these upcoming industrial cameras. It's a 5 megapixel sensor, it can do single shot imaging, so this is something that is industrial grade. You can put it on the industrial production floor and it will withstand the conditions. There is somebody to replace the camera if it breaks, you can simply buy a new one or replace it quickly. And they have a high frame rate to do inline inspection. So if you go to, let's say, glass production, that's something that they're doing, let's say, with 5 per second. So 5 objects per second racing by, and you capture 1 image each and make an image of that. What is lacking with these cameras right now is the software. So they have some software to do colorful images, some of the manufacturers, but what you still need is an extension and plugin, a module that is able to give you some measurement values. And what you want to have is a calibrated measurement, for example, of the retardation. So how much is the light retarded or delayed going through the glass? And this is something that you measure in nanometers, and this is something that people working with glass are familiar with. So they want to have this number, and this is something that needs to be calculated and calibrated. And what the demo shows, what we are doing here is we are able to measure the magnitude of retardation, so how much stress is in this piece of glass, and we are also able to measure the orientation of the stress. So in which direction in the bottom of the glass is the stress oriented. I mentioned the Argo project. From doing that, going from Scilab to a DLL to a product, one solution would be to reprogram everything again. That's not what we propose, what we should be doing. We were very lucky to join this Argo project, and I would like to give you an idea of what we have been doing, what the whole consortium has been doing there. It's WCET, Aware Parallelization of Model-Based Algorithms for Heterogeneous Parallel Systems. That's quite a lot of words in this title. WCET is worst case execution time. So the idea is you want to make sure that you have an algorithm and you go to the next step in modifying that automatically, that it guarantees you real-time performance, hard real-time performance, that you can be sure no matter what happens with the input, you get a defined output at after a certain delay of time. And this is something that the compiler tools that have been developed with the partners here are able to do. Then the next step is, in this project, it's a transfer to parallel C code. So you put in some code, it can be Scilab, it can be other code, and it goes to a parallel implementation of your program. So it gets distributed around multiple cores and still ensures that it's real-time capable. And it is able to use parallel architectures, let's say CPU with multiple cores or some other types of multi-core architectures in the FPGA, for example. It's a project that is still ongoing, but almost finished, and we were able to use part of this tool flow here to work in this idea. As I mentioned previously, we started with the Scilab algorithms for processing the raw images. We had them implemented and we're using them, and we used one of the tools here. This is the MTrix Parallel Studio that goes from a first step of making your Scilab code into a C program. And this is part of the Argo, so Argo works on that and refines it and even optimizes. That is not yet included here, but at least the first step is included here. So the algorithm automatically is converted into C, and this is compiled together with Visual Studio into a DLL, and this DLL is then included into Halcon. Halcon is a software that is used in industrial inspection scenarios. So let's say if you have something on a conveyor belt and you want to inspect some object passing by. Halcon is one possible way of doing this. It interfaces to an industrial camera, gives you the image, gives you tools to work with those, and allows for real-time deployment in the factory. So by providing tools. And what we are showing back there is the demo of starting from the Scilab code, going through all of that automatically, and finally putting the result directly into Halcon. It's not without manual interaction, so you need some interface code to go with that, but the algorithm itself goes through that chain. And I think this is a major step forward for us, because if you're in research and development, you're constantly trying to modify the algorithms and changing this, changing that, and it's much easier to do that in Scilab than to do it in C. So what we provide finally as a result of that is a software as an Halcon extension that can be used with all industrial cameras. So we don't care which one it is in this case. It is able to calculate the polarization values from the raw data of the camera, and let's say the degree of linear polarization, angle of maximum polarization, Stokes values. And it goes further in the example we will be showing here. It's the glass parameters, so retardation, magnitude of stress, orientation of stress. And the demo we have there, it's similar to this one. It's a light source, a polarized light source. We put the glass on top and have a camera on top. The camera goes into the PC and does the processing and shows the result in real time. So I would like to invite you afterwards at the coffee break maybe to have a look at this, how this comes together and how we are using the whole process. In this demo, we are processing the raw image. We are getting to the intermediate Stokes values for polarization, and then calculating the glass values afterwards. That already concludes my talk. I was talking about polarization imaging. This is a modality that is quite new from my perspective. It's known in physics, but it's not really known in the applications yet. So it's something that is upcoming, that is coming to more and more applications. It requires quite a lot of application-specific tuning and processing. So it's not easy to go from one to another, because quite a lot of those is quite different. And as a summary, the last part is the Argo tool flow, where you can go from Scilab to software that is coded or implemented, and in this case, even up to the point of product delivery. So that is something that could be used in an industrial context, as we are showing here. Okay, so that's it from my side. Thank you for your attention. So, maybe question, quick question?
Yes, actually I was going to propose that. If anyone has a question, Butter?
So in real industry, the measurement result is something where you can sort out the glass. So if you detect that something has gone wrong, you can throw away the glass and only pass the next glass. And this is done for many aspects, like if there is a bubble in there or a stone, then you discard the glass. And this is a process that is, so discarding the glass, that's what they know and what they're doing right now. And this is simply another modality they are testing for. So it goes into an inspection machine, and after the inspection machine, there is a pusher that throws away the bad glass. Based on a threshold maybe, or on some other metric.
Polarization methods are very much used in geology. You observe and analyze the rocks.
Mm-hmm.
How do you see incoming? How do you see the perfection that could be made with Scilab?
So I have not been dealing with rocks lately yet. So there is some disciplines that know polarization for quite some time. So that's the life science, biology, mineralogy. They have polarization in their microscopes. And that's what they have, and I don't think this technology is improving that much. But we've had people discussing the idea of mining, for example. If you're mining or having large amounts of rock, so to say, and want to sort them or want to detect something in them, polarization can help and go forward. I'm not sure if there is a direct request to Scilab to include polarization right now. I think the major challenge is that if you have an industrial camera, it's going to be hard to interface it, to put it in there and get it into a live workflow, to put it into industrial production and have everything go through Scilab. I think that's not that common yet, maybe.
I think, yeah, the three aspects that I would see here as a benefit for a larger audience is, first is image processing, I mean more traditional, I would say, not so specialized, but for everyday purposes, I would say. So image processing is the first, as you mentioned. There could be some improvement in all of what goes around classification, maybe all of the machine learning algorithms that could come and enhance those capabilities in image processing. And the last point that you mentioned is also connection to the hardware. So that would be, and that's also one of the things that you presented in your presentation. So yeah, okay. I don't know if this helps you in any way for geology. Okay, thank you, Michel.
Okay, so thank you.
So our next presenter, Stéphane Jiménez, doctor. Wait, so that I can shortly read your introduction. So, Stéphane, you are working at ArcelorMittal Global R&D as a project manager for digital knowledge management. Your current project and activities, you've been working for 9 years at ArcelorMittal, design, implementation, and management of the Diabolo solution, so that's what we will see today. exploratory project, scientific computing and digital knowledge management. So it sounds very relevant to our subject. Your education, you have a PhD in computer science for physical modeling and simulation of complex deformable body, 1993. And you worked at the laboratory Leibniz, previously LIFIA, Laboratoire Informatique Fondamentale et Intelligence Artificielle. And you graduated from Grenoble INP, Institut Polytechnique de Grenoble. So Stéphane, you have the stage.
Okay. Good morning, everybody. So I will tell you the story of what we call Diabolo. In fact, the title is not on this first slide, so I will pass to the second. What we call Diabolo, which is the global framework we set up in ArcelorMittal R&D for support and manage the full life cycle of scientific models. And in fact, I'm here because we choose Scilab as a pillar for this global system, and we will see how Scilab has been fully exploited for the main component of this framework, but also to distribute and reuse model in the factories. So near 10 years ago now, some people involved in knowledge management in R&D in ArcelorMittal decided to tackle with the problem of the poor management of model life cycle. The fact is that a lot of R&D models have developed, numerical models are developed in R&D for 30 years now. These models are very heterogeneous in technology, in structures. They are developed by people geographically distributed. And these models are used and maintained by many different users over the years. The result is that they are not easily shared nor reused. They can be instead redeveloped, partially redeveloped. And the model life cycle is very hard to manage. In fact, we constate loss of knowledge, of digital knowledge, and we have a huge time from conception of the model to industrial use of this model. So we decided to tackle with this situation and trying to develop, to set up a whole framework to ease the model sharing and reuse, to ease training and use of this model in a multi-domain and multi-physics simulations, and to finally support the full model life cycle of these models. So, in fact, the solution has been, we imagine as a solution to set up a real gateway between the conception of the model in the R&D world and the final use of this model in the industrial situation. So this gateway relies on three basic components. First, standards and methods to be able to pass from exploratory works to standardized and certified components that can be used by the whole scientific community, but also by the industrial actors. Around this standards and method, we build a model repository, a central model repository, where every model will be committed and will be achieved for every users. We also developed a simulation platform when all these models can be used together by every research engineer, and all this is supported by a lot of tools that has been put at the disposition of all the users. The expected result was to support all the model life cycle from the initial conception to the final use in industrial situation, and considering that this model will have to jump from step to step, being in the first conception, initial conception, the model is full mathematical scientific expression of the problem. Then they will have to be refined to be fitting and to be adapted to the industrial situation, and then finally perhaps to be optimized or even be used to produce a surrogate model for the use in a real-time industrial situation. Thus, based on this consideration, we started to build some 6 or 7 years ago now what we call the Diavolo solution. So the Diavolo solution is first relies on a centralized model repository and a depot. It says that, in fact, in a centralized repository, every research engineer will publish, in fact, its model as an executable component, be it developed in C, Fortran, Java, Scilab, or Python, or even as Excel sheet, for which we will make tailored custom wrappers, in fact. And so it publishes its executable component, but also the scientific documentation that accompany, that make his work usable by other colleagues in the research community. Then he will follow a model publication workflow and describe every part of the technical specification of its model. In fact, it will describe the interface complying with the standards we set up for the platform, and it will also enter all information so we need it for the end user to use correctly this model, to understand how to use it and how to feed it with its own data. Then the system will be able to use all this information described by the user to generate all the gateway needed to have, in fact, this model available as an Xcos module that will be then so compiled, packaged, and published in a depot. So every user will be able then to synchronize its local platform with the models that has been published in this centralized depot, and then use potentially every model that has been developed and published by any other research engineer in the community worldwide. So when, of course, you understand that this global platform is based on Scilab, of course, even if I not precisely mention it. So we develop, we set up, in fact, an atoms depot in the ArcelorMittal intranet. And this depot is completely dedicated to, in fact, research model developed by ArcelorMittal research engineer. They will also find some specific tools that have been designed and really imagined for the day-to-day use of the research engineer, for their analysis, for their study of sensibility, and in fact for all the technical assistance they have to do for the factories, which are in fact the customer of the work of research engineer in ArcelorMittal. Then they will be able to retrieve and install any of these tools and any of the published model. The model will come as a full operational Xcos toolbox, along with the help, using the help system, and so the user will be able to directly access the information needed to use correctly this model in the whole system. Diavolo is also a powerful and user-friendly toolbox set. He said that, in fact, the model will come with a sophisticated inner diagram. In fact, it's not only the model itself, but we developed a global multiplexer that make possible to reconfigure fully, in fact, all the entry data port of the model. It says when the model is at the initial conception, the researcher have to use all the process data needed to modelize the phenomenon and to calculate the solution. But when we are making a dedicated study, sensibility of a particular use of the model, we don't use to feed all this data of this model, or you even want to feed them in a different way, in different orders that they were conceived in the initial conception. So this system will, with this system, the researcher will be able to completely reconfigure all the data entry and for input and output data with a graphical interface, creating new data ports, distributing data in any of these ports, and hiding or showing any of the part of the data for the model. Some advanced block also comes with user-friendly interface. It's a we have packaged, in fact, optimizers and other analysis tools, and they comes with a Java user-friendly interface, so that any end user can use this sophisticated tool for his day-to-day use. And we also develop some specific blocks that permit to develop direct specific simulation blocks by trying some programming or making some specific analysis, or, for example, inversing a model by using some traditional techniques to make the inversion of a model, and so on. Thus, all this tool, with all this tool now, all peoples concerned with the development and the use of numerical scientific model in ArcelorMittal R&D can use in a very simple graphical way all models that have been published by their colleagues. They can chain these models, making complex simulation schema involving every model, but also all the tools that have been put at their disposition for data access, for parametric studies, and also very powerful blocks for making optimization or reverse analysis of their models. We also have developed a lot of sync blocks in order to visualize all the results. They are really dedicated to the day-to-day analysis. For example, sensibility analysis is something that is very, very often used. So we have developed some tools really dedicated for this kind of analysis and packaged for this. So making very easy, in fact, the day-to-day use of the platform. Thus, what is Diabolo today? Well, global R&D in ArcelorMittal is distributed worldwide. So you can see that we have quite a laboratory in each continent. It's a population of 1,400 peoples. Among them, in fact, more or less 300 people are concerned by the development and the use, day-to-day use of numerical models. So Diabolo today is really used by, so it's something like, yes, 7 laboratories worldwide, and each one giving its contribution, in fact, in development and publication of their model. Some ones are very dedicated to automotive model development, other ones are dedicated to product model development, and some to process modelization and simulation. So the ability to connect in the same simulation environment, process simulators and product model development make really a great opportunity to in fact, to develop some very useful process and develop also some advanced scientific study. Let's focus now in the second part of my presentation on some very interesting advanced use cases that have been achieved with the Diabolo platform. So the first one is what we call the building physics simulator concept. In fact, the idea was here to set up a multi-domain simulation in order to tackle with the physical properties of a building in order to optimize, in fact, its performance in terms of life cycle assessment, energy consumption, and sorry, Microsoft is making me some, okay. And by using, in fact, all the models already existing of different parts of a building that have been previously developed by R&D, and putting them all together to make a sort of global design of a building, and then optimize all the global design using a multi-objective optimization block that have been developed previously for advanced design system studies and optimization in automotive field. So this block, what we have called Optim Advanced Design System Toolbox, has been previously developed, an exploratory project. It's a conjoint work between ArcelorMittal R&D and INRIA. It's a multi-objective optimization module based on surrogate model construction. He will use a non-dominated sorting genetic algorithm to optimize this surrogate model, and then non-dominated solutions are extracted using a Pareto filter. He relies on 3 additional Scilab toolbox: DACE, that is the Kriging model implementation in Scilab for the generation of the surrogate model. We use SVM-KM to reduce the number of variables of this surrogate model, to order and reduce the number of variables. And then the NSGI2 algorithm is used to fitting this surrogate model. Then the block will enter in a cycle, iterating and building, refining at each iteration the surrogate model, and then optimizing the global design system that has been set up under the optimizer. So a GUI has been developed to set up this block that is really complicated, even if all the processes are making very automatic. In fact, the user here has only to define the variables of his optimization, the objective of his optimization, and the boundaries of each variable objectives. He will be able to program a projection, a discrete projection of his design of experimentation. It says sometimes, of course, the space of solution could be discrete, but the optimizer will obtain some continuous solution. So we'll have to make projection on your discrete space of solution, and it will also be able to program constraints on the solution in the form of, in fact, logical relation between the different objectives. Then the purpose was so to use already existing modules to simulate some particular aspect of the behavior of a building. The first one was what we call ACE, which is a free available module that has been developed by ArcelorMittal Building R&D. This software deals with, in fact, the footprint structure of the building, and we'll be able, from a footprint, to design for a footprint and the span of in each direction, to, in fact, calculate the total weight of the structure, selecting the good beam corresponding to all the charge of the global bâtiment, and also calculating the total weight and the total price of the structure. We also used some models, as you can see, developed and implemented in Excel, to calculate the mechanic and the thermal properties of the facade, while the global project definition was just entered by the user. He has to give some information about the building use, will it be industrial or habitation use, its time life, its localization, the type of facade, the percentage of opening on the facades, and the kind of heating and cooling system used in the building. Then, in fact, the optimization module will be simply used to generate the optimization variable will be the grid span in both directions and the thickness of the facade component. Two other aspects of the building that has been simulated was the energy consumption. So the global structure and also the thermal properties of the facade can be used by a software, a commercial software that is called Transys, that is really dedicated to the simulation of thermal performance of building. Has been used, so has been monitored from Scilab to calculate the energy consumption for heating and cooling. And then another module developed in Excel by R&D was able to calculate the quantity of CO2 and the primary energy demand for this same building. So the whole data computed by the different module has been used to set up the objective of the optimization module. It's a CO2 emission, total cost of the building, and energy for total heating and cooling. The result, the global pillow schema has been completely set up and calculated in Diabolo. The optimization process is fully automatic, and it's fortunate because, in fact, a full simulation lasts about 20 hours. So we start up the process, and then just coming back at after some hours to see the global result. The design of experimentation is completely saved at each iteration, and we are able to restart, in fact, the simulation at any step. So, in fact, you can add hours and hours of simulation, refining your result. And then, in fact, we have found that some very original combination of span and thickness of the facade that absolutely not correspond to the traditional way of designing a building, showing very best performance, a better performance than the one that can be constituted. So it's very promising, and all this work is currently used in the setup and the programming of professional modules that I cannot speak about today because it's still confidential. So I will just let you imagine how we can use this kind of result to really set up a professional module, end-user module to, in fact, optimize and calculate the global performance of a building. Steel frame building, of course. Okay, let's focus on a second advanced use case of the Diabolo platform. In fact, one of the purpose in the life cycle, one important step in the life cycle of a model, when they start to be used by, in fact, the real customer of R&D, it's people in factories for day-to-day expert analysis or even for the use in the production process. In this case, in fact, the purpose was to release and, of course, quickly release some models for process to be used by the expert in the factories. So, in fact, once we have the model completely packaged as Xcode toolbox, they also come as gateway for Scilab. So we are able, in fact, to distribute them as a module. And so we set up a global architecture using the module issuing from Diabolo as, using, the Scilab engine, computation engine, to run these models and a graphic interface to monitor, in fact, the execution of the model according to the data that have been entered in fact, a very graphical, rich graphic user interface. So, Scilab engine has the model for model running. The models are directly distributed as Diabolo modules, so it's very easy and quick to retrieve a module and to plug it behind the facade of the application. We develop a generic Qt widget to capitalize, in fact, in the development of graphic components because they are coming back. Even a lot of models use, in fact, the same concept. So this widget can be reused a lot of time. And some models, in fact, and some combination of models, because behind this facade, we have sometimes 3 or 4 models that are chained, in fact, as Diabolo modules. And finally, they represent the full simulator of a process tool, like, for example, hot strip mill. And in this case, the graphical user interface has been really sophisticated and dedicated. You can see really graphic manipulation of the configuration of the different cage, of the different steel cage. Okay. This way to set up and to package the model has significantly speed up the model delivery process. In fact, we have now 20 single or chain models deployed in factory in this way, and more than 200 users using the model issued from Diabolo, but behind this kind of graphical interface. Let's focus now to end this presentation of the third use case, the statistical model toolbox. In fact, we develop, in this case, we will see that, in fact, the cycle is complete because, in fact, the models are conceived, refined in R&D, and then deployed in an industrial platform to use in online qualification of products. So it relies mainly of a Diabolo toolbox that have been ported from S+. In fact, S+ is a commercial implementation of the R language, so statistical language. So for numerous years, in fact, a service in R&D, which is called Quality Product, dedicated to the study of quality product, has developed this statistical toolbox in S+, that is able, based on the Vapnik model, is able to automatically generate linear regression from process data by selecting the most influent data and performing, in fact, the most efficient linear regression considering a set of process data. The generation is completely automated, and the toolbox allows also the optimization of the model, and it comes with a lot of analysis and filtering tools that help to correct the process data, to refine the model generation, and so on. It relies on three additional toolbox: the ScilabTec to calculate the linear regression, the NAND toolbox for clustering and correlation, and XLSLink to make some report and data import. In fact, the whole generation of the model is based on the use of the Vapnik model, which will be able to sort data according to their influence of the variance. In fact, it's ANOVA analysis, and thus it will select automatically the data that have to be retained for the better representation of this set of process data. Thus, in fact, the whole toolbox have also been deployed as a graphical application, Windows application. Thus, in fact, the process engineer in the factory have its own installation of the tool, is able, from its process data, to set up the first version of his linear or pseudo-linear model. Once the result is okay, correct for him, he can export the whole project to its colleague in the R&D lab, which will be able to retrieve the project, to refine the model, be it in the application or in Diabolo, because everything are completely compatible and can work in each environment. Thus, he can also optimize or really refine this model. Then he will be able to deliver this model in a configuration management system. This configuration management system will be then used to update the platform that are deployed in the factories to day-to-day quality control process and automatic product qualification for the production in online. Of course, these models are statistical models, so they are constantly observed in statistical process control, and once the user can state a derivation from the result, because in fact this model calculates mechanical characteristics, and sometimes some trials are made of the products, so we can compare the result of the model with the trials. And once we observe a derivation, we enter again in the full cycle, resetting a new regression, and then validation by the researcher and publication in the configuration system management. Okay, so this was the last slide of my presentation, and I want just to say how we are very interested, of course, of further development in Scilab. I saw some conjunction in the axis. Model reduction is for us really not for system optimization, but really to have surrogate model to be used online in real time in the factories should be really an advantage. We are focusing, we have set some exploratory project in this domain. We are also very interested in standalone application generation, because as you see, we have in fact two populations that may exchange the research engineer and the quality process in factories, and they need to have this kind of possibility to set up full graphic application to be used by end users in factories. And of course, optimization tools and optimization performance are also a great concern for us, because we are deeply using this kind of module. Scilab V6 is the current subject. We have ported all the statistical toolbox has already been ported to Scilab V6, and Diabolo, it will be the task for the next year. to port it to Scilab basis. Okay, thank you. If you have some questions.
Thank you, Stéphane. It's a wonderful presentation. I discovered
it's
a
a
few
lot of
things.
years of work. It's not.
Yeah. I saw some of it in the previous presentation from, I think, 2011, 2013.
Yes, yes. All right. The full story of Diabolo, the Diabolo framework, has been presented for the first time. We were just setting up the first version of the toolbox in 2011.
Now I see some of the PIDO. I think this is new, the process integration design optimization, right?
What is interesting is that the community, the resist engineer community, has really taken the tool and is using it day to day now. So you can say that we have 100 users of Scilab, indirect user of Scilab in global R&D in ArcelorMittal.
Well, that's great. Do you have maybe from the audience some questions around statistics, optimization? We have an expert here, so if you have questions about that. Anyway, we have a Q&A also later at the end of the day, so if we want to discuss about, you mentioned model reduction, some application development and so on, so yeah, we can address that in the end.
Okay.
Thank you, Stéphane. So we have one last presentation, and afterwards we will have a session meet the expert at our break. So if you want to register to ask some questions about model reduction, here we have an expert on optimization and such simulation subject. Hughes, also related to XCOS, there's Clément who's here. So if some of you are using some of the system, dynamic system modeling, and Antoine also is here for everything that goes around Scilab, the architecture, even Scilab Cloud. So you can register. I think it's, yeah, just outside. So here, it's on the entrance. You can register. So the next presentation is from my beloved friend Jean-Pierre, Jean-Pierre Beauvais. So let me shortly introduce you properly. Well, I should know all of this, but I'm going to read it anyway. Jean-Pierre is an engineer from a very famous French university, Arts et Métiers. He has a PhD and is currently working on energy projects, helping companies cut their energy bills. After 30 years with the pharmaceutical industry, R&D, production, corporate, in the last 15 years, he has been working on process control and HVAC. Yeah, it looks like it's a current concern for us, HVAC. Sorry for the cold. But at the time where a critical global warming is looming on the horizon, with a 3-degree increase expected by the end of this century, it is paramount to look for any means to curb this devastating trend. Yet not demonstrated that humanity will survive this episode. It's quite dark what you're writing. Huh? So we can state that many companies' life are already at stake, sometimes even not being aware of this imminent threat. While optimizing energy production is one of the most common responses, cutting energy demand is far less addressed, yet presenting a largest potential in terms of potential savings. Energy Cut delivers consulting and advice on the best way to cut energy demand fast with demonstrated payback for both the enterprise and the planet. It looks like a good agenda for today. So that's it. Tu veux aussi la page web? Ah d'accord. Tu veux aller sur Scilab Cloud? Je vais directement.
Tu es admin?
Si groupe.
Tu dois être admin?
Oui, c'est pas ce compte-ci.
Si tu avais laissé un truc derrière.
va le laisser charger. Tu veux commencer par la présentation?
Non,
tu...
je vais commencer
par la démo.
Non, je vais commencer par la présentation. Pardon, je vais commencer par la présentation.
Alors, attends. Pendant ce temps-là...
Thank you, Jan, for your kind introduction. So, let's talk about energy, something very necessary today. Okay. Let's have a look to energy over the pharma industry first. Okay. Well, so these are figures from Sanofi, my former company. Manufacturing amounts to 30% on average of the total energy that is consumed in the company. And climatization, HVAC, standing for heating, ventilation, and air climatization amounts to 60%. Lighting for 10%. Say nothing. So, gas amounts for 53%, electricity 47%, say 50-50. And now, if we look at other competitors in the pharma industry, we see that the main clients are respectively production, R&D, surprisingly, and packaging, bottling packaging. In pharma industry, we have actually two big areas: chemistry, that manufactures the API, active pharmaceutical ingredient, and the second part of the industry is packaging, tableting, filling, packaging, all these activities. Wow. So overall, 50% goes to electricity, 50% goes to gas. Motors amount to 70 to 80% of the total electrical consumption. And HVAC amounts to 60 to 70% of the total consumption. So it's a major part of the energy that is consumed by this industry. This is valid as well for other activities like cosmetics. And the food industry is not too far from these figures. Let's have a bit look into the technologies. So heating is done using heating coils, a kind of exchanger, cooling coils, hydraulic distribution to convey the fluid to the coils. This is done through networks, valves, pumps, all that. Fans, okay, to supply the air into the rooms, and fans to extract the air from the rooms. Fans that are geared by motors, electrical motors, with bad or good efficiency. Control systems that are really paramount in this area and that can bring very terrible performances sometimes. And air filtration, especially in pharmaceutical area and in electronics, by example. The quality of the air is paramount. You know, when you are manufacturing injectable products, you can imagine that we do not want to have any particle. So the number of particles in the air is severely controlled. And due to that, the air is filtered accordingly. And, of course, to be sure that we have exactly what we want in terms of regulated parameters, we have to take into account temperature, that is somehow critical for some process, the humidity, critical as well, the air change rate, and the pressure that guarantees the avoidance of particles. And we have to take into account the pace of the work in the plant. Okay, what is exactly HVAC? Okay, as per regulation, okay, it's a need to supply the air meeting some specific requirement on temperature. By example, for tableting, everybody knows what are tablets. On average, the temperature should be below 27 Celsius grade. Relative humidity under 60% on average. For effervescent forms, it's under 30%. The air change rate in offices, by example, as per regulation, we must have 2 volumes per hour and per human. And the air purity, and this boils down to particles again. Okay. This is a typical air handling unit, with fresh air incoming here, with a damper here that can be controlled. Red means controlled, you see. So the air is incoming through filters, then going through a heating coil, which is controlled by a valve. Then it is it goes through a fan, the supplying fan, a cooling coil, another heating coil, and sometimes a humidification, which is again necessary, and then incoming into the room. So the room is has various characteristics like its size, the tightness, the insulation, and a number of controls are performed, such as temperature control, relative humidity control, pressure control, and air change rate control. So it's a pretty complex system, you know. Well, the air is extracted by a fan, and a part of this air is recycled here through a damper that can be controlled as well. And more or less big part of the air is extracted through another damper here. Okay, so we were facing in the company, we were facing this challenge. We were facing a big source of energy consumption with the awareness that big savings were possible, but not knowing how to start and what were the most critical parameters to address first. We had a look to the market, and we were unable to identify an easy model, easy tool to put that in any user's hand, to be able to quickly figure out how to start, which parameter were the most critical. So because the factors are very diverse, they powerfully interact. There, of course, on top of that, linearities are numerous. We have in this model more than 40 equations. And, as I said already, no tool was available. So that energy managers were saying, okay, you asked me to do something, but actually, I don't know if I have to improve the fans, if I have to look at the fluid distribution network, if I have to speak with quality regarding the parameters. So we realized that a tool was necessary. And it was the beginning of this decade. And this is the way we address that. At the beginning of this decade, we first decided to build a draft. In my mind, it was clear that it was only a draft because it was done with Excel. I will come back on this point further. And it was pretty complex to build this tool. And some simplifications were necessary because of the limits of Excel already. However, we were able to qualify the tool and to validate it with some real examples, so that, in spite of my reluctancy, this model was deployed based on Excel, was deployed by something like 2013. It was deployed on a very reduced number of sites, and we were lucky because it was really a mess to be able to manage the deployment of such Excel-based model. The size of the program and the data was already beyond 200 megabytes. So you see, we were having some problems with our infrastructure in some countries at that time. So next year, we decided to rebuild the application, and this time based on Scilab. Scilab was the main contributor for the project, except for the algorithm for the calculation itself, but it's a small part of the program itself, something like maybe 10%, no more. And we first deployed a local solution based on a very usual deployment, but it was not very easy to manage due to the updates. Numerous updates were necessary. So that 1 year later, we decided to transfer the application that was running pretty well to the cloud. And I think this application was the very first application for Scilab to going to the cloud. It was done very quickly by the same dream team, and the application is hosted today by ESI, and or by Google, but via ESI. And the deployment started in 2016, very quickly. So that today we have 52 sites regularly connected and 92 users, registered users, who day to day are using this tool. We are going to see how it works to cut their energy bill actually. The decision was made this year to extend the usage of OptiClean to other companies. So, so this is bill, well, the energy bill that is cut. Okay. All sites were able to cut their energy bill by 2-digit savings. So it's already a big success, and sometimes reaching 50% of savings, and even more in some special case. And nobody was able to believe that before starting. And not only this company, but all those companies have this huge potential with HVAC. So, how they did that? They first started to question the parameters, okay? The dead band on temperature, on relative humidity, because the very facile excuse was, I'm not guilty for that. Quality asked for that. Okay, just please call quality. And quality was saying, I never asked something so accurate, you know. I just want the temperature being below 27 Celsius grade. But what was really implemented at the plant was 22 Celsius grade plus minus 0.5 Celsius grade. This is just terrible in terms of savings. Okay, the smallest, the dead band, the largest, the expense in energy. The air change rate was questioned as well, because in some plants for manufacturing the same product, in 2 different plants, some were using 60 volumes per hour, while others were using 30. So why having this discrepancy? 60 is a huge waste of energy. And the implementation of eco mode at night, out of working hours at the weekend, was as well something very important and considered. So this was done without any investment, meaning that they were able to cut their energy bill by sometimes 20% and sometimes more, not investing anything, just discussing with the quality department. And the second time, they decided to modify the technology, so improving the temperature control, temperature and humidity control. We should teach people here how to do. And improving the fluid network efficiency as well. Increasing the motor efficiency, the gearing, all that. And sometimes, as a secondary effect, very positive secondary effect, they avoided to invest in unnecessary chillers, transformers, boilers, and so on. Okay. Okay, here investment was necessary. So now, quick demo. Where is it? Could you help me?
Yeah, it's here.
Okay. Thank you. So here you can see the data We have data on the room itself, on, oh, it's in French, sorry. On energy and control, air handling unit with volumes per hour. Okay, so I prepared a demo. And we have energy recovery as well. It's a bit okay. The cloud is far. Optically means the cloud with diamonds, you know? Optically means, you know? So, okay. So let's see at the room. The set point on temperature, humidity, the size of the room, insulation of the room, all that. And since time is running, let's calculate demo effect. No. So, more than 8,000 times, the algorithm is executed hour by hour over 1 year to be able to calculate what is the consumption of energy. And the consumption of energy is represented by the cumulated energy over the year with heating, with cooling, and with black ventilation. Here are the results as figures. Okay, this is consumption of gas, electricity. You see the figures are already significant.